Hey everyone, welcome to the USGS Landslide Hazards Seminar. I'm Stephen Slaughter, and this meeting is hosted by the Landslide Hazards Program. The seminar is a twice-monthly presentation by researchers, academics, students, and professional geologists from private industry and government agencies who are working on some aspect of landslide and landslide science. The seminar is co-organized by Matt Thomas, Jamie Kostelnick, and me. The presentation is about 15 minutes long, and at the end, you can submit questions via the chat window or use the raise your hand feature in combination with a microphone and video camera. We typically wait till the end of the presentation to take questions. During the presentation, please remember to keep your microphones and cameras turned off. Today's speaker is Karina Swarovski-Dario, who is a USGS research geologist based in the California Bay Area. Karina works across the United States and territories on a variety of field-based geomorphology projects that investigate sediment erosion problems and landslide hazards. She's also part of the USGS USAID Landslide Disaster Assistance Team, working on landslide technical capacity building with foreign partners. Karina started at the USGS as a Mendenhall Research Fellow in 2016 after receiving a PhD from the University of Oregon. Prior to graduate school, she was a Science Policy Associate for an Earth Science nonprofit in Washington, D.C. Welcome, Karina. The virtual stage is yours.
All right. Thank you so much, Stephen, for that introduction, and thank you all for having me here today. So I'm going to talk to you today about landslides triggered by Hurricane Maria. And from this initial aerial image that you see here that was shortly after Hurricane Maria, you can already get a sense of why it was easy to call this an extreme event. There's a high density of landslides that affected people and infrastructure for months or more. There's a wide variety of styles. You can see on the left here a much deeper slide and some weathered soils, and then many shallow, long run-out slides throughout the area. So I'm going to walk you through the initial USGS and the ongoing response to this widespread landsliding event. And the initial focus was on mapping and for identifying the highest hit areas and those that would still be at risk. And then this transitioned to an island-wide inventory to help improve or calibrate hazard models, and we're now working to create an updated landslide susceptibility map for Puerto Rico. Now, I am just the messenger. There are lots and lots of people, as you can see here, who have worked or are working currently on this project. I'm going to focus on the field response since that's where I was mostly based, but I want to touch on as many aspects of this project as I can, because there's a lot of great science going on, and I wanted to highlight all of it. So I'm peripherally involved in many of these projects, but again, as a warning, I'm by no means an expert in all of them. So I'm going to go through a quick explanation of all of these different projects. I tried to call out the folks or the pubs on the slides as much as possible, so I encourage you to reach out to them if you want more information. So let's start with kind of just a reminder about Hurricane Maria. So the landslides from Hurricane Maria followed the actual hurricane, which made landfall on September 20th, 2017 as a Category 4 hurricane. That's not happening right now. There were landslides in most of the 78 municipalities, and that's how Puerto Rico is broken up by municipality. So most of them had landslides. And there's likely at least 250 millimeters of rain, and this followed Hurricane Irma, which was a couple weeks prior. There is a total number of landslides that we've mapped now is over 70,000, and these landslides, as well as the associated issues with power lines, water, roads, isolated communities for days to months. There's no power to much of the island for about 6 months. And landslides aren't uncommon. This happens twice a year or so. You get storms that can generate landslides. So the USGS role in all of this was kind of tackling this unprecedented scale in both the hurricane and the landslide, this like extreme event. The focus, like I mentioned before, was this rapid response. We are providing technical assistance first and foremost to FEMA. And then growing out of that was taking this a step further to complete an actual inventory and advance models and improve our understanding of landslides in Puerto Rico, and trying to improve upon the susceptibility maps that were existing. So a big part of this work was collaborating closely with stakeholders and partners, and the focus was to identify what the primary needs were, so letting them drive what some of the science is, as well as what the interests were on the USGS side, as well as leveraging just the variety of expertise we have across the USGS. And so going back to Puerto Rico, let's get everyone oriented with Puerto Rico itself. So it's an island in the Caribbean, and it's a small island in the Caribbean. It's about 50 kilometers by 100 kilometers wide. It has about 3 million people. There's a big population in the metro area up here, but about a third of the population is scattered through this mountainous region. You can see this high elevation belt that runs along the spine of the island. Your highest rainfall is over here in the Sierra de Quillo, which is about 3 meters per year. And then kind of the land uses, a lot of this land has been developed for agriculture or forestry. And I love showing this next slide. There are roads everywhere. Speaking of land use, it's one of the 9th densest road networks globally. And this is only the official road network. Anyone who's been to Puerto Rico knows that you could probably roughly double this with the number of farm roads and other unofficial roads that there are out there. So a lot of areas of this landscape have not been untouched. From a geologic perspective, you have the Puerto Rico here, sandwiched between the Caribbean plate moving roughly this direction about 2 centimeters a year, and the North American plate moving this direction. There are a couple of major faults that cross the island, but actually the faults are fairly poorly understood, and only recently has there been LiDAR for the interior of the island. And this is a bit of an outdated and kind of blurry slide, but the most recent earthquake was off in the southwest corner here. So looking at the actual geology, before we kind of tour across the landslides, the general geology of the island is that the central spine of the mountainous region in here is a mix of intrusive and extrusive rocks. You've got some granodiorites and these light greens, and you have some mixed volcaniclastics and these browns. And then on the flatter edges, you have these uplifting carbonates and alluvium along both the northern and the southern coast. All right, so that's your quick primer to Puerto Rico. So going back to the landslides, what we started with when we first arrived about a month after the hurricane was doing it called landslide triage. The idea was to identify the hardest hit areas and determine if there are additional areas still at risk. That was the most pressing concern right after the hurricane. There was additional rainfall coming, and are slopes fully evacuated? Are there big deep-seated landslides that might go? So that was the initial focus. We started by trying to identify where those hardest hit areas were by creating a density map from satellite and aerial imagery in the weeks following the hurricane. And then we field checked that by driving and aerial reconnaissance. So that initial landslide density map you see here, and this was later published by Aaron Bissett-Gurton and others in GSA Today. This initial map was just a gridded plot of the island. You had a 2 kilometer by 2 kilometer grid, which are each of the boxes you see there. And it was a quick look in the aerial imagery. Okay, are there roughly over 25 landslides per square kilometer or under 25 landslides per square kilometer? Because with 70,000 landslides, we quickly discovered you couldn't map everyone really quickly. So this was the best option we had for getting at where are the heaviest hit areas. So you can see from this map, there are some key areas that highlighted right away. So this is this Utuado region in central Puerto Rico. This is Naranjito over here, and this is Lares and Las Marias on this side. So about 10% of the island had this high elevated landslide density. Right. So giving a quick tour through those 3 highest hit areas. First up, you see Utuado. So again, this is that central region in the mountains here. And these had mostly shallow, sandy, fast-moving landslides. And this is from the cover photo that we started with. You can see it again here. Just high density of fairly shallow landslides. A lot of them impacting some of the major reservoirs that are in there. And this is a pretty major highway. I mean, it's a two-lane highway, but a pretty major road in Puerto Rico that you can see has been reduced down to one lane. And this is about a month afterwards, and there's still piles of sediment all along those roads. Moving on to Naranjito, which is a little bit further east for here. The landslides here are typically a bit deeper. They're more in weathered clays, but there are still fast-moving landslides and many coalescing landslides. So you can see here, there's this dark red weathered soils. A lot of these coalescing landslides that were very hard to differentiate which one was separate from which. And a lot of them impacting ridgeline houses and then running out the valleys. The last area I'm going to tour you through is Lares, which is again over here on that further left side. And these were typically a little bit deeper. They're very rocky, very fast landslides. You can see how deep it is here. It took out this road. Some of these slides running down into the rivers here. And so these were the highest hit areas, and this is the areas that we decided to focus more of the detailed mapping and susceptibility maps that we're going to make. So we'll come back to those areas later on. But again, from the first standpoint was, let's get out there and let's get a best of an understanding as we can of these landslides. So in those kind of months following the hurricane, a group of us got out there and we did some detailed field mapping. We cataloged about 200 landslides in the field, and we found that they're mostly in soil, often at that soil and saprolite interface. And they're typically kind of tens of centimeters to a few meters deep. And they often transition to long run out debris flows or coalesce. And as a reminder, we're working in a tropical environment, so the time sensitivity of this data is even more important than usual after landslide events. The vegetation comes back with a vengeance very quickly in this area. So the first few months are really key to getting that data that you couldn't see otherwise, kind of characterizing the source areas, characterizing the runout, characterizing some of the materials. So now trying to think about what were the parameters that might have been driving some of this. This is, again, that density map, so that gridded map that you saw earlier, that was the dark red and the light red, but now it's just a hashed pattern. So that cross-hatched are the greater than 25 landslides per square kilometer, so that high density area, and then the empty squares at the lower density area. And looking at by slope, which is our common predictor of where you'd expect the most landslides, it's not a really good fit. I mean, take this with a grain of salt. Everything here is quite steep once you get into the mountains, but this is one of the steepest areas, and your actual high density was in a slightly lower steepness region. The other common predictor is rainfall, and the density of slides doesn't seem to match up with that very well either. So again, you have those crosshatched, which are displaying a little bit harder to see on this one, but again, those crosshatched areas are here and here. They kind of verge into the highest cumulative rainfall areas, and so this is some data from Ramos Sharon and Arima from UT Austin. And again, you got to take some of this with a grain of salt because rain gauges are not the best at recording rainfall when you have horizontal rain and the radar was knocked out during Hurricane Maria. So this is, again, kind of the best estimate we've seen so far of that rainfall. But those, again, by this estimate, the heaviest hit areas are in the center here, and our highest density landslides are kind of offset from that. So the last thing to think about is, okay, is there a geologic formation that seems to be highlighting? And this is where you start seeing a better correlation. So Utuado area in the center here really nicely highlights this granodiorite batholith that you see over here. So there may be some correlation with geology, with the soil type, and these are the sort of things that we're going to keep exploring and I'm going to talk to you about in this talk. So kind of putting that all together, how can we better understand the hazard? So this was kind of the motivation. We need to relate some of these parameters that clearly aren't matching up in the general sense. It's not really just rainfall or slope that you would think first. So what are the parameters that can estimate the likelihood of failure? And obviously, and many of you on this do this all the time, there are many ways you can look at this. You can look at previous failures, you can use regression models, frequency ratio, or just use numerical or physical models to predict the failure from soil or hydrology or topographic inputs. So thinking through all that, this is where the projects evolved for the USGS for Puerto Rico. So kind of there's three main categories of what's being done out there. The first was thinking about landslide hazards from a regional to an individual landslide perspective. And we started touching on this when in the tour that we've given you so far, is we did an inventory of landslides remotely and in the field. We started doing some material characterizations, and we're starting to think about that in a greater context of the history of landslide recurrence and geometry and geomorphology, which I'll touch on at the end. The next kind of topics are thinking about the timing of the initiation of this, the hydrologic thresholds, and what this all means for storm-driven slides. So this has led to field monitoring of the subsurface conditions and modeling of the conditions for likely conditions for landslide initiation. And kind of putting all the above data together, the field data, the initiation models, and some new refined runout models, trying to produce some new susceptibility maps for Puerto Rico. So walking through those different steps, it all starts with information, with making sure people also know what's going on. So kind of as we were getting started with all of this, one of the first things that was done was getting an initial characterization of those types of slides into a guide for residents. So this is a landslide guide that was produced by the Natural Hazards Center based in Boulder, Colorado, as well as with the USGS and the University of Puerto Rico, Mayagüez. So together, this team developed this outreach materials based on and the preliminary understanding of the landslide hazards, and use this material as outreach to kind of bolster the understanding of what the potential hazards are in Puerto Rico. And from that, we're trying to develop then better susceptibility maps and better understandings of what that actually means from a mechanical, a process standpoint, from the science side, essentially. So the other initial work, which was also led by University of Puerto Rico, Mayagüez, was to go beyond that initial density map, the initial gridded map, and actually identify each landslide headscarp. So with a finer resolution, how can we improve that susceptibility map? So the map you see up here is a bunch of points, actually. Those aren't polygons. Each little piece of orange is a headscarp point. And so this was every single landslide that occurred from Hurricane Maria that we could identify, or the University of Puerto Rico's dedicated team of students led by Stephen Hughes could identify. So they identified 71,431 landslide points. And so this is a great initial inventory to use. And if you are at all interested in looking deeper into this, there's a open file report out by Stephen Hughes and Bill Schultz, as well as this point database has been released in a data release as well as a GIS layer. So when you take that point inventory and you look at it by density, it has that same pattern of landslide density. I'm going to jump between the 2-week version that we did as the initial grid and the one from the 71,000 points. And so one that's comforting, it's great to know that the initial 2-week version identified that same pattern of landslide density as opposed to the 2-year point density. But now we have this great data set of 70+ thousand points to work with. And so how can you take that and make a better susceptibility map? And again, just need to figure out a way to relate the parameters to the likelihood of failure. And so from the old landslide maps, they painted a lot of Puerto Rico red, which, yes, there is probably some susceptibility in most parts of that, but that's not very helpful from a planning standpoint. This is a map from Monroe in 1979, and it was mostly a hand-drawn map using slope and some soil properties. And they mapped most of the island as the least moderate susceptibility. Kind of building on that, using a frequency ratio based susceptibility map, Lepore et al. In 2012 tried to make an updated version of that based on these kind of 3 study areas where they added a few extra parameters to their map, and again updated very high, moderate, so 3-phase susceptibility map. The idea is to kind of take this same idea and see if we can improve that with the 70,000 points. So Stephen Hughes and Bill Schultz also used a frequency ratio based approach. They assume that the future initiation sites will be triggered by similar conditions. And so the idea is to try and figure out what conditions are most predictive. So using a ratio of the number of landslides at any particular parameter to the total number of landslides by the area of that same parameter over the total area of the island. And so they looked at a variety of different parameters and then log transformed those values to create a susceptibility index. So you see the susceptibility index here for soils, for slope. And when they looked at all of these different parameters you see listed here, they found that soil was actually the most predictive, followed by soil moisture, and then slope came after that. And so putting that all together, they aggregated that total susceptibility index, their SI values, to calculate an area under the curve. And basically your area under the curve, again, represents that degree or measure of separability. So if all your parameters can uniquely identify things, you're going to have no overlap and your area under the curve is going to be 1. As you have more false positives or false negatives, that number starts going down. And then your ROC, again, is your probability curve related to your area under the curve. So when they weight their various SIA values by slope, and then they modify that with soil moisture, they find their best fit. And from their models, they found their best fit by combining all those things, and they tried to eliminate the bias from this being like a particularly extreme event. So the resulting susceptibility map is what you see here. And again, this is published in the open file report by Hughes and Schultz. And they got an area curve value of 0.9 based on those testing with the points that those 70,000 points. And they thresholded things by basically the percentage of pixels that were in each of the categories. So you can see this is broken out a little bit finer than the initial 70s map that painted everything red. So this is out there for an initial use, but still trying to improve on this. So we're going to try and go beyond that point data. So taking this a step further, can we incorporate mapped and attributed landslide polygons to calibrate landslide hazard models? So Kelly, Backstrom, and Mason Einbund, as well as Bill, have been doing detailed mapping, again, in those 4 regions, well, the 3 regions that we've been talking about before, Lares, Naranjito, and Utuado, as well as some of northwest Puerto Rico. And they have these detailed inventories of about 4,500 landslides, and they've mapped the total affected area, so it's no longer just a point data. It's the total affected area, as well as the source areas broken out, the headscarp points, and the whole travel paths. There's also attribute tables included with each of these polygons that describes a large number of things, but things like vegetation type, the land use, the mode of failure, if it impacted infrastructure. They've created a really great database to work from. And so all of that data is available on sciencebase.gov. And so there's a variety of recent data releases by Kelly and Mason and Bill that is available for anyone to look through. So kind of building on that, we also want to understand, soil moisture seems to be important. What are some other factors that seem to be important for generating landslides that we can monitor actually in the field? And so this has led to installing a network of landslide sensors, monitoring stations across Puerto Rico. So there's an initial two. You're not meant to be able to read this, but just get the general distribution of these. The initial two were here in central Puerto Rico that were installed soon after Hurricane Maria. And that was by Joel Smith, Matt Thomas, and Bill Schultz put those out. And you can see some detailed information on those initial installs in Joel Smith's data release, as well as Matt Thomas's paper. And now the ongoing work is to keep putting out stations to make the target, I believe, is a network of 12 stations, and there are 10 that have been installed so far by Bill, Kelly, Mason, Emily, and I've gotten out there too to help them sometimes. And these stations are recording in near real time rainfall, soil moisture, suction, pressure head, and that's going to be also a great tool for testing out some of these models. So we've particularly been focusing on soil moisture because that seems to be, from our initial work, our most reliable measure of where high density landslides occur. So this is two figures from a paper from Aaron Bissett-Curtin, others. This is in that GSA Today paper. And so this is down here on the x-axis is that density of landslides. So this is the high landslide density, so that dark red on the gridded map, the light red to no landslides. And trying to look at that with rainfall, which is all the circles, that's kind of all over the place. But when you look at it with soil moisture from map data, you see kind of a nice progression of there's a increasing with landslide density. So it seems like soil moisture might be one of our more reliable measures of landslides density. And again, over here, this is the SMAP data broken out in the time leading up to Hurricane Maria, which you see here. The red, again, is that high density. The yellow is that low density, and then the gray is just island-wide. So going into Hurricane Maria, it was already elevated. They're kind of coming out of a drought in hurricane right before Hurricane Maria. And you can start seeing the high density landslides and the lower density landslides kind of pulling away from the island-wide data. So Matt Thomas has been incorporating this into the idea of there's maybe a potential better thresholding model for understanding when landslides might occur. And so I'm sure we're all on this call familiar with the general intensity duration curve, where the idea is with higher intensity and longer duration storms, you're more likely to generate positive pore water pressure and thus have conditions that would trigger landslides. Another idea is that potentially you need to reach some sort of threshold antecedent moisture before you pass this critical point. So you need to be somewhat wet, and then you need to rain before you can generate that positive pore water pressure. So Matt took the monitoring data, some field data from the hydrologic conductivity, and putting that together was looking at how these hydro-meteorological thresholds behave for Puerto Rico. And kind of the big take home from his paper is that for seasonally wet areas, so this Utuado region that I've mentioned before, where it's really coarse soils and it kind of dries out and then gets wet again, incorporating your antecedent moisture is actually outperforms that intensity duration model. So here you can see the positive pore water pressures are nicely boxed over here once you exceed about 50% soil moisture. It does not perform so well in the perennially wet fine soils. So the big takeaway is that soil hydrologic properties matter. And the long-standing idea for Puerto Rico was that the soils must remain wet for most of the year, and so antecedent moisture actually doesn't really matter. And so what Matt's finding is it seems to, well, there are more soils that dry out than people anticipated, and that incorporating soil moisture would be important. So you can check out his paper here in hydrologic processes. So kind of building on the soil moisture, you need to think about how deep your soil is and where your soil is too for initiating landslides. So and it's especially important in Puerto Rico, where most of the landslides seem to be at that soil saprolite boundary. So Rex Baum and others have estimated the distribution of mobile regolith, or soil, on the hill slopes and calculated a factor of safety to estimate where landslides are most likely to initiate. So they use this steady state soil model, regolith, calibrated with the field data, and that you see on this bottom image here, where the darker colors are deeper soils that you can see accumulating in the hollows. And then this was used as an input to estimating a pressure head and a quasi 3D factor of safety for during heavy rainfall. So the factor of safety values then were thresholded by 75% and 90% of the map points to make a very high and high likelihood of initiation. And so all this is kind of also going into a new USGS software that's in prep, Slabs 3D, which both regolith and triggers can be inputs to. All right, so we have a potential idea of where landslides might initiate, but let's think about then the mobility of slides. And so again, Mason and Kelly have since mapped much larger areas in detail, but we initially started with mapping these 4 small areas that span the island to assess some of the basic geometric and topographic parameters of these slides to get a sense of how mobile are they, how many headscarps are coalescing, and to get a sense of what the runout potential really is. So we started with these 4 areas, and we found that about 10% to a quarter of them had multiple source areas. So you have many heads feeding into one larger polygon. And these multi-point slides account for most of the area. And when you're looking at that from a mobility standpoint, so here we have 2 H/L graphs. So H/L is on the y-axis here, where you have lower numbers of H/L mean higher mobility. So on this graph, higher mobility is up this way. On this one, higher mobility is down this way. So looking at those 4 different regions broken out by geology type, if you look at just the bar on the far right for each of these, that's the actual H/L values from the map landslides. You can see that that these marine volcanoclastics in red and those granodiorites were the most mobile of all the slides. We're trying to compare this with rainfall, which is what you see on these other plots here. When you look at this with the number of headscarp points, so the number of headscarp points are growing across here, you also see that the mobility increases with increased headscarp. So increased coalescence, increased mobility. But the other takeaway from this is that, even if these are more mobile, there's a large range of mobilities in each of these areas. And so that's kind of the challenge when you're thinking about runout modeling. So the next step, we've started landslides, we've thought about how they started to move. Let's see how far out they go. So that initiation and the runout are both crucial for identifying high hazard areas for Puerto Rico. And as you probably remember from the pictures at the beginning, the hazard was high on the ridge tops. You're impacting where a lot of the houses are, and the impact was high in the runout zones down where you're crossing roads, impacting power lines, other infrastructure, or potentially running out in channels and turning into really hazardous debris flows. So like I was showing on the mobility plots, you have everything from things that just travel partway down the slope or things that mobilize into far traveled debris flows. So just looking at this line, you have some really long traveled map polygons here, as well as little short things all in the same area. So to put that all together, we need some sort of estimate to run out to some way to estimate runout for non-channelized topography, as well as for channelized topography. So in this case, can use that H/L idea for non-channelized topography. And then once they reach any of these transporting material reaches a channel, can combine some empirical volume area scaling relationships and debris flow growth factors to estimate that. And so this is work that Diane Bryan, Mark Reed, Colin Cronkite Ratcliffe, and John Perkins have all been working on to develop some updated runout modeling tools. And one of the things they're working on is Grfin tools, which is a new USGS software package that's under development. And Grfin tools combines all those pieces together. So you can have a user-specified source zone, and then you can have an initial transport calculated by the HORL from tau DEM. And then if any of that material reaches a channel network, you can calculate a channelized runout with a growth factor. And that's the Grfin part. So the growth, flow, and inundation to make Grfin. So for Puerto Rico, they've been running this over those three municipalities, Utuado, Lares, and Naranjito. And for this, they're using Rex-Bominals, their initiation zones that I mentioned earlier that were calculated using regolith triggers and SLAB 3D. So that identifies where landslides might start. And then Diane, Mark, and others have been looking at how far those might run out once they reach the channel. So the picture you see here is from Diane's GSA poster. And you see that they have outlines of some of the most mobile slides here that were mapped in the field. So those black outlines. And then the purples here are the debris flow runouts. So they tried to threshold those into a dark purple and a light purple as more and less hazardous. And they use those as the best performing scenarios from the Grfin that they tested on a subset of the most mobile slides that were mapped from Hurricane Maria. All right, so that was a lot of different steps, and I went through quite quickly, but putting it all together, the goal of this is to make, again, those updated landslide susceptibility maps. So we're incorporating the mapped and attributed landslide polygons, using that to calibrate and validate landslide hazard models, and putting that all together into some updated landslide susceptibility maps. So the ongoing work right now are these maps are going through review and getting ready to be published. And they're creating landslide susceptibility maps that identify that initiation, transport, and deposition zones, putting everything in one map. This combining the updated storm-driven landslide slope stability models, Rex's realm, with the updated runout models, Diane and Mark and Colin's realm, and calibrating and validating that with the field data and landslide inventories. So there are draft maps in prep for Utuado, Lares, and Naranjito. You can see the example draft map here for Utuado. Okay, so that was a quick tour through all of the parts going into the landslide susceptibility work. But taking a step back now, kind of thinking about this in a larger geomorphic and climatic context, what might set the stage for these landslides? And so this is, as having a geomorphic background, this is like where also I get really excited is, what does this all mean from a bigger standpoint, from a longer term standpoint? I mean, the first question is, was Hurricane Maria a one-time occurrence? I mean, we had a sense that it wasn't, and that was worth putting all this work into it, but it's definitely not a one-time occurrence. This is a very frequent occurrence on Puerto Rico. So you have a hurricane, as you can see on this image here, which frightens me every time I look at it. You have a hurricane transiting or grazing Puerto Rico about every 25 years. And you don't need a hurricane to create landslides. So you have widespread landsliding about every 5 years, and just at least some landslides every kind of 2 years. And looking at this plot on the right, this is again on the x-axis kind of the number of landslides. It says widespread landslides, frequent, isolated, no landslides. Looking at rainfall, and these are just two different measures of rainfall. And so if we think that the updated Maria numbers are correct, and it's more like up here in the thousands, you can also get widespread landslides, kind of a much smaller level storm. That's kind of the takeaway from this plot. So landslides are a common occurrence here, common and can be a widespread occurrence here. So what might be setting the stage for all of this? can we think about anything about the landscape that might give us a better clue about the recurrence interval of this, or what's setting the stage for the material that is failing? So kind of the two big questions that we're looking into now from the kind of geomorphic perspective is, does landscape evolution set the initial control on landslides? And potentially, has Hurricane Maria reset the availability of material to fail? And we're looking at these in the Utuado area because it was both one of those heaviest hit areas. It has a fairly uniform geology. It's all underlain by that granodiorite batholith. And that has a really interesting geomorphic topographic history. You have these perched plateau up here with thick soils and deep landslides, and these highly dissected side slopes that have really shallow landslides happening on them. So kind of the question is, how much does that play into what style of landslide you have, the frequency of landslides? And then when you're thinking about these thinner soil mantled side slopes, when you have a Hurricane Maria type event that has this huge density of landslides, have you just denuded the soil so much? Have you wiped it clean that you're now at bedrock? And so another Hurricane Maria that happened today would be actually less impactful. So those are the kind of things that we're thinking about now from a geomorphic perspective. So one of the landscape evolution questions that's being queried by John Perkins and Monghan Wan at University of Maryland are using shallow geophysics to understand the long-term landscape evolution and what sort of short-term hazard implications there are with that. So we've recently been out both on this plateau area and on the side slopes and performed some seismic refraction and electrical resistivity surveys to look at that deep critical zone development. And that critical zone development and that conversion of bedrock to saprolite to mobile regolith sets that boundary condition potentially for shallow landslide failure. So the goal is to model how the strength and hydrologic properties evolve. And here's some preliminary results from two of the refraction line profiles. So this is up on the plateau. So again, up on this thick soiled area. And this is on the side slopes down here. And the takeaway from this is that the 1200 line is typically the dividing between intact bedrock and saprolite, is equally deep in both of these, about 20 meters deep. But this kind of slightly weaker saprolite, the 600 meters per second layer, is much thicker in this plateau area, and it's much thinner on these side slopes. So this is ongoing work, like I said, that's that John Perkins is looking at. The other aspect, and a part that I'm most curious about, is what is the availability of that material to fail? So how are we generating this material? How are we generating the soil that is failing? So the goal is to understand the material properties and the rate of mobile material is generated and what implications that has for landslides. And so this is also ease into work that Bill Schultz is interested in. And so we've been taking core samples for material properties, digging pits for weathering profiles, and taking stream and hill slope sediment for cosmogenic dating. So the idea is, from a geomorphic perspective, what you see up here, right, is there's ideas about soil production functions and how quickly you might develop a thick soil profile. And from you see here, Bill, and you can kind of see Mason here doing some cone penetrometer measurements. And they're finding that, most of the soils on some of these side slopes are about 1/2 meter thick. And that's from our mapping in the field as well, as we're finding that most of those, the average depth of failure was about 1/2 meter. So to generate that kind of 1/2 meter soil thickness from kind of the erosion rates we think there are happening here would be several thousand years. So what does that mean when you have hurricanes happening much more frequently than that? So you can start playing some games with erosion rates and thinking about the percentage of landslides. This is all a hypothetical graph here of how those might increase your erosion rates, or how they might increase then your conversion of material to soil. So lastly, kind of thinking about that from like a chemical weathering and a hydromechanical properties of that material, we've again been taking samples, and Bill's been running them for looking at the strength properties, and I've been looking at the clay development in those to think about, you know, how might this affect where stuff is tending towards unstable? Like, are there actually clays that are developing at that half meter depth? Is the porosity changing? So it changes how water flows into the subsurface? So starting to think about all of those things to kind of think on a more granular to landslide scale of what's affecting, what's providing material that's then more readily unstable. So kind of the fun way to think about this too is we also have erosion pins out there, and we've been monitoring those over the last couple of years, and we've been seeing these landslide scars fill in. So we put these pins out there, and they're now filling up with alluvium in there, and then they're filling in at a rate of about 10 millimeters a year. So when you start putting all this together, you start thinking from a geomorphic perspective. Your soil is being produced potentially over millennia. The erosion pins are filling in at 10 millimeters a year. So to get to that half meter would only take about 50 years. And then when you start thinking about the amount of landslide material is evacuated and the recurrence of hurricane-driven landslides, things are probably happening on a century type time scale. So that's kind of the things that we're trying to tease out. What's dictating the availability of material to fail? So again, this is all ongoing, and it's very arm wavy at this point. So, but stay tuned for more on that. So with that, that was a really quick tour through all the different things that we're working on related to Puerto Rico. So again, this was just an unprecedented scale, both in the hurricane magnitude and just the number of landslides. So we capitalized on that by doing a rapid hazard assessment and data collection. And we're utilizing those initial data sets to calibrate and improve initiation, runout, and hydrologic threshold models. And again, all this work is closely working with partners and stakeholders for both things that they want on the ground, as well as just involving them in all of these steps. So another takeaway is that the size and style of landslide seems likely tied to geologic as well as human history of these sites. So I urge you to check out all the recent papers I listed, check out ScienceBase if you want to play around with any of this data, and keep a lookout for the many landslide hazard maps that are forthcoming. And then the ongoing work again is really diving into what is this human short-term and geologic long-term history that might affect the frequency and style of landslides, and what contributes to the location and the mobility of those. So with that, I thank you for listening, and I will take any questions, and will do my best to answer about any of this, or call on those of you in the audience to help answer the parts that I'm not as familiar with.